So the plan is the first few classes I'll try and give basically as much of the proof of our recent bound on Ramsey numbers as possible, and then we'll move on. So the first few classes will be filmed. Okay. Let me begin by reminding you what Ramsey numbers are. So R of k, minimum n, such that for every coloring of the edges of the complete graph in red and blue, there exists a monochromatic copy of kk. Okay, and I will always write MC for this, but I'll probably also just say red and blue lots of the time. Okay. Right. And Ramsey's theorem, 1930, says that this thing is always finite. Okay. And I'll give a proof for this. I mean, I guess you all know the proof, but I'll give a proof for this, partly to motivate the way we're going to think about the problem in a minute. Okay, so the next question is what decent bounds can we prove? So Ramsey didn't give a bound in his paper. I think he says something like, oh, maybe it's like at most k factorial or something. Not really sure where he got that from. But Mehdi Sekaresh proved that it's at most 4 to the k. Right, and then there was a long gap. So I guess I should say it's worth writing the lower bound as well. So Edish and Sekaresh prove it's at most 4 to the k, and Erdush in 47 proves at least square root 2 to the k. Yep.
Question: Did people have a better, worse bound before Erdős proof in 1927? Or?
So apparently, right, you can take the Choran coloring, right, for a silly lower bound. And apparently there was actually sort of conjecture, don't know exactly how widely believed it was, which gives what k minus 1 squared plus 1, that this was actually the right answer. I mean, probably it's pretty hard to construct anything better, right? So even to get k cubed, you need this a clever idea and some linear algebra stuff, like Frankel-Wilson type stuff. Yeah, so even beating this, I think was not known, and I think it was actually a bit of a shock that this was really the case. Right, so the proof of the lower bound, just to remind you, is just take a random coloring. Okay. Take a random coloring, count the monochromatic KKs, expect a value less than 1. Okay. So the problem from then till now is to improve either of these numbers, root 2 or 4. So let me just mention. So there's some history. So Rödel proved some sort of improved by improvement here. Was like a polylog. Thomason improved by a root k. This in the 80s. Actually, basically simultaneous. And then there was another long gap till Conlon in the 2000s, got an improvement of a super polynomial improvement. So an e to the log k squared over log k, which in particular is much bigger than k to the c for all c.
This is the list of denominators.
Yeah, so improved by a factor of this. Improvement factor. And then, right, so perhaps I'll just state SARS as a theorem. It's very recent. So he showed the Ramsey number is at most e to the minus log k squared, some constant in front here, times 4 to the k. Right. So an improvement over Conlon was just remove this log k. Right. And these three later works use an approach introduced by Thomason that took advantage of quasi-randomness properties of colorings that, with Ramsey numbers close to this bound. So suppose the Ramsey number is very close to the bound, then your colorings must be like super, super quasi-random, so then you can take advantage of that to find structure. Okay, so main theorem we're going to try and prove. Maybe I'll move this up.
Do you know what riddle to get this?
Right, so this is unpublished, but in a survey paper by Graham and Riddle, they prove a bound of log k plus l. And basically the idea, if I understand correctly, so it means you're trying to deal with some Ramsey number, k versus k or something. You take these Erdős-Székely steps, and this would end up being sort of k versus 1, this would end up being 1 versus k. You wander down, you have no control of where you're going, but at some point you get down to some sort of, whatever, 3 against t or something. And Erdős-Székely would say, okay, well this is at most t squared, but Aitai, Komlish, and Semerady gain a factor of log. So if your t is like, what would you expect your t to be if you're walking randomly? Like root k. So then you'd gain like a log root k, so a log k. Okay, so the only way you fail is if this stays super, super close to the middle. But then, okay, maybe you can just try and force it away from the middle a bit. This is how I understand Riddle's proof to be. So I didn't actually read the details, but right, so it makes sense that using Aitai, Komlish, Semerady, you would gain this kind of polylog factor.
Okay, thanks.
Right. So, the theorem, which is by Marcello, Simon, myself, and Julian, which says that the Ramsey number is at most 4 minus epsilon to the k. So there's some explicit epsilon for which this is true for all sufficiently large k's. So epsilon, epsilon the constant. And the epsilon we get is something like 1 over 100. So we have two proofs of this actually, both sort of, the first part is the same, and then there's a different way of finishing. One gives like epsilon is 1 over 1,000, and the other one gives like epsilon 1 over 100. So I'll explain both of them as we go along. And these epsilons can be improved with some more sort of more careful calculation. Perhaps more interestingly, there's a different approach that we were unable to make work, which really might give a better constant. So I'll also try and explain that. But that probably perhaps at the end of the series of lectures. Okay. Okay, so first things first, let's see how to prove Erdős-Székely. And I'll do it in a way that perhaps motivates what we're going to do later. Right, so we're going to try and prove Erdős-Székely, which is r of k is less than 4 to the k. Okay. Right, so the idea is as following. So we're going to describe their proof as an algorithm. So rather than as an induction as sometimes done, or I'm going to describe it in a slightly different way. And I'm going to draw some pictures as well. So we're going to have two sets, A and B. I'm going to have a set X. Okay. have red and blue, I hope. Have some red and some blue. And A is going to be a red clique, and all the edges are going to be red as well. And B is going to be a blue clique, and all these edges are going to be blue as well. Okay. So at the beginning of the algorithm, A and B are empty, and X is everything. And each step of the algorithm, we're going to choose a vertex of X. We're either going to add it to A or to B. And how are we going to decide which one we add it to? Well, just based on the number of red or blue neighbors in here. Okay? So any vertex we add here, at A, there still stays a red clique. We have to replace X by the red neighborhood of that vertex. Okay, so what is a step? We choose X in A, and we either add either A goes to A union X, or B goes to B union X. Right? Okay? And then X is just defined to be the intersection of the red neighbors of A and the blue neighbors of B. Okay? In this proof. Is everyone happy with the definition of the algorithm? This is depending on, this is if has size at least x over 2. Sorry, maybe I'll. This is the problem with filming, is I'm not allowed to erase these lines. Apologies, I'm going to erase the lines. I'll go ahead. Right. So this is, I'll just do it here. If the red neighborhood of X intersection X is at least x over 2, and this is if the blue neighborhood of X is at least x over 2. And OK, so I guess if you're a computer program, you'd complain that this is not exactly a partition, but OK, don't worry about plus minus ones. Okay. Okay. So what happens? So I'm going to go through the proof, sort of motivating the later calculation. So what do we need to figure out? We need to figure out how long the algorithm goes. How do we do that? We just look at how big x is. Okay. So the observation is that the size of x is at least by this 2 to the minus a minus b times x. Right? And the algorithm ends when this is less than 1. So at the end of the algorithm, this implies at the end of the algorithm, a plus b is at least 2k if n is at least 2 to the 2k. So at the end. Which implies that the max of A and B is at least k, which implies there exists a monochromatic kk. Good. So just to walk through everything like super slowly. Okay. So the point is that because we're looking for a monochromatic, a red kk or a blue kk, these sets just have to get to size k. Right. Okay, so what's the next idea? So what's the idea to try to get started on improving this? Well, the idea goes back at least to Thomason, and I don't know if it even goes back earlier. So at least to Thomason. Perhaps I won't go say that. Thomason or earlier, I'm not sure. Which is the following. So try to find a large monochromatic book. Okay. I think Erdős and people were studying books sometime before this. I think there's books papers, extreme vulnerable books, 70s? Yeah, so I mean maybe they were motivated by this as well. It's an interesting thing about thinking about this problem. It's in the course of the last few years of thinking about it, we've bumped into all kinds of sort of useful things that people have developed over the decades, which suddenly sort of fit in somewhere in. And I'm sort of curious now about lots of them about whether they were motivated by thinking about this. So it seems to connect to lots and lots of different parts of combinatorics. But anyway, so here's this idea. So here's what a book is. A book is, I'll do in blue, I'll do in red, because I'm always going to look for red books. So let's start as we need to go on. This something looks like this. I mean, it looks like one of these guys, right? This is a big red book. You have a red clique, and then look at the common neighborhood. The common neighborhood are the pages of the book. Okay, so you sort of think of this as being like the spine of the book, and then these are the pages. So, yeah, why would that be useful? Well, suppose this set here has size at least. So now I need a definition. So maybe I'll write it first. Okay, I'll write the definition here. So let's recall definition of RKL. So we're immediately sort of sent to think about this thing. RKL is the minimum n such that for every colouring of the edge of the complete graph in red and blue, there exists either, my red and blue again, a red copy of KK or a blue copy of KL. Okay. It's an asymmetric version. It's all familiar for everybody. And so for us, L will be at most K. Okay. I'll always be looking for red KK or blue KL, and L will be at most K. So just in case I forget to say it. Okay, so what about if this set is bigger than R, K, K minus T, and this has size T? So why are we happy? So Lucas already replied to this question in Simon's talk, so someone else should tell me.
So actually, the second color is red.
Right, so this is symmetric, so it doesn't matter. But yes, thank you. Yeah, so I wrote it like this because I want L to be smaller, but yeah, okay, fine. Or I'm tricking you, so you want to find, you don't know what to look for. Yeah, okay, right. So here, what do we want to find? We've already got these T vertices in red, so here we only need to find a KK in blue, or a KK minus T in red. Right? And if we have at least this many vertices, then we can find one of these two, and then we're finished. Okay. So, how large is this number? Okay, well, let's recall some theorems. So, in fact, Erdős-Szekeres actually proved RKL is at most K plus L choose L for all K and L. Actually proved K plus L minus 2 choose L minus 1, but that kind of stuff won't matter for us. Just to note that that SAR proved e to the minus log k squared times this if L is of the same order of magnitude as k. Okay, but the proof breaks down when L gets smaller than this. So the method of Thomason and Conlon and Saar, so Thomason proved a thing corresponding to his result. Conlon proved this with over log k, and Saar optimized. So now I should say, let me write all of them. Thomason, Conlon, Saar. Right. Getting this. But this also won't really help us. So we'll just be using this bound. Right. Okay. So how large is this thing? So it's at most 2k minus t. Choose k minus t. Okay, so we're starting out with 4 to the k minus a little bit less than 4 to the k. And we're going to find a book with this many pages. So it matters to us how this relates to 4 to the k, which is basically 2 to the k choose k. Right? How much smaller is this than this? Okay, so let's do a little calculation. I'll do it here. Sorry? Yeah, exactly. Good question. Yeah, so how large is t? I mean, so this works for any t, right? So if we can find such a thing for any t, we've won. But we have to think how large we want t to be. So we'll see in just 1 second. Okay, so how do these two numbers compare? Let's do it up here. Yeah, so note that 2k choose k is 2k minus t choose k minus t times, 2k minus t plus 1 dot 2k, k minus t plus 1 up to k. Right, just by thinking about the factorials. Okay, that's kind of ugly, so let's simplify it. All of these things are roughly as big as this first one. Right, more or less. So this is roughly equal to 2k minus t choose k minus t times, so this is a factor of 2. So it's something like, okay, let me write it first. 2k minus t over k minus t to the t. Maybe if you want to be a bit more precise, it's more like that. But again, I don't really care at the moment, right? Just to give us an idea. Okay, so if you're multiplying these factors, this is like 2 is something a bit bigger than 2, bigger than 2, right? So all these factors, they're all sort of roughly of the same order of magnitude as this last one. Right?
Why t over 2? Aren't all these factors close to 2?
They are, but this is also close to 2.
But
I'm saying, yeah.
If we divide the exponent by 2, then it would not be close to 2 anymore.
Sorry. This guy's close to 2.
Yes.
Sorry. You're quite right. Thank you very much. You're quite sensible. Yeah, sorry. So let me do an extra step and then, So just to be approximate, right. So this is approximately, same thing again. So we have a 2 to the t, and now we're closer, right? Now we're more like 1 plus t over k to the t, and now I should put an over 2 here. Yeah, but I won't, because it's just... Right, and this is basically e to the t squared over k. Okay, as long as t is roughly small. So just being very approximate. E to the t squared over k. Okay. So what does that mean? So when we're finding this book, think about we're looking for this book over here. And suppose instead of doing some half red and half blue, we did only red steps. For the first t steps were only red. Right? Then you'd get a thing here that was 2 to the minus t times n. Okay? Just losing a factor of 2 each time. 2 to the minus t times n is now bigger than this, right? By this amount. In fact, we could even decrease n by this amount and still be bigger than this guy. Right? So, is that clear? So this implies that if n is bigger than e to the minus t squared over k, 2k, choose k, and we do t, we find a sort of t 2 to the minus t times n book, then we win. Does it make sense? So if in each of these t steps we manage to keep half the vertices, then we've improved the Ramsey number by this amount, by e to the t squared over k. So now to answer Xifei's question, we would like t to be a small constant times k in this argument, if we can get it to be this large. Okay? So Thomason actually conjectured that you could do this, that you could find a book of this size with t even, I think, I'm not sure exactly how large it would, but yeah, at least a constant times k. Yeah, he got an extremely strong conjecture, which is still open, which would give a much better bound actually on the Ramsey number, if it were true. Okay. So let's say we are not going to prove this. Okay, we do something a bit different, but similar. Okay. All right, but this is the basic intuition, that you would like to sort of just lose a factor of 2 each time, and if you can get to small constant times k, you're already happy. Okay, so yeah, so we'll put this over here. This. Some conjecture of Thomason. You can find a book. We'll call it a T book with 2 to the minus t times n pages. Approximately, like, okay, maybe slightly fewer, but basically that. This is still open.
So, sorry,
Yeah.
conjecture that you can always find this book or, I mean, because the argument is the rent, or is it
Yeah,
either
so-
you find the monochromatic clique or
So right, so yeah, so we're going to do something a little different. So if I understand correctly, if I remember correctly, Thomas' conjecture is just you could find a monochromatic book of this size. Yeah, monochromatic. Okay, so let's go about starting to try to find this book. How are we going to find such an object? Okay, so we're going to be inspired by the Eddy-Sekeres proof. So we're going to try to mimic this. Instead of not just finding this, having this x, we're going to also try to find a book. There's a natural way to do that. So, next idea. So let's have a set A up here. I'm going to draw B down here now. I set X on the left. And as before, A is going to be a clique, a red clique. X means red neighborhood. B is a blue clique. X is blue neighborhood. But now we also want a book. So I have another set on the right called Y. And let's make sure that we have all of these red edges. So we're already doing something different from Thomason, who was trying to find a monochromatic book in either color. We're not looking for a blue book. I mean, I guess we're sort of constructing one here automatically, but this is not our aim. This is where we're looking for a book. We're looking for a red book, or a red clique, or a blue clique. These are the three things we're hoping to find. Okay. So the first idea, perhaps in that we had, was to try and do this thing asymmetrically. We're going to introduce this asymmetry right from the start. basically just because if you're trying to find a book in both colors, you don't know what to do. You don't know, you're trying to get red and then you're trying to get blue. It's better just to pick red and go with it. So we're just going to go with red. Or at least it makes things simpler. Better is a strong word, but simpler. Okay, so we have at least some way to get started. Right. Okay. Yeah, so what we'd like is to design an algorithm that does this. Okay. So, what kind of moves have we got? Well, for a start, we have, I guess, the two Eddy Sekeres moves. Right, so our basic moves are as follows. So one is a red step. So what does a red step involve? You take a vertex from X and you put it in A. Okay. Choose X in X and replace A by A union X. Okay. So your basic red move. And then what do we have to do to keep the conditions? We have to update X and Y. Right? So B can stay as it is. B just stays as B. X has to be updated to be the red neighborhood of X intersect X. Right? And Y has to be updated to be the red neighborhood of X intersect Y. Right? Because we want to keep these conditions. We want everyone in A should be complete in red to X and complete in red to Y. Is it okay? So we take this X, we're going to add it to A. So we need to look at this red neighborhood here and its red neighborhood here. And replace X by this guy and Y by this guy.
Oh, at the beginning, how do
Please.
you separate the X and Y?
Thank you. Yeah, that's a good question. So we're just going to so for the algorithm, we're just given a partition.
Okay.
But what do? We take a coloring and we take a random partition, a random equipartition, let's say. And what we're going to want, what we're going to care about actually, this will come up in just 1 minute, is the density of red edges between X and Y. That's what we care about. That's all we care about. Okay. Okay, so when is such a step good? Well, I guess we'd like the red neighborhood here to be at least sort of X over 2 maybe. And we definitely want this thing to be at least Y over 2. Right? Because that's, oh, I erased it now, but it's what we're hoping. We're hoping to find something, at least at the beginning, we're hoping to find something of size 2 to the minus 2. Right? So every time we add a vertex to A, we can afford to lose a factor of 2 on the right. Okay. Maybe on the left is a bit more flexible because we're not going to use any of these guys in the end, right? The only purpose of X is to make sure we can run for a long time. Okay. So can we do this? I mean, yeah, maybe there's a vertex that has high degree in both sides. Or maybe there isn't. Right? Maybe there's lots of blue over here. Or maybe there's lots of red over here, but low blue across. Or maybe the size of these two things are anti-correlated. Okay, there are various things that go wrong. But at least this is our sort of hope. Okay. Okay. What about 2? 2 is okay, so we do a blue step. Yeah, so I'm not describing the actual algorithm yet. I'm just trying to motivate it. Okay, so we'll get there slowly. I'm not even sure if we'll state it today. So. Okay, so what's a blue step? Well, it's similar. You would choose X in X and update B. So put X in B. Okay? And then we have to update the rest. So now A stays the same. X has to become the blue neighborhood of X intersect X. And Y becomes, to check if you're awake,
The same.
Y, exactly. Y doesn't change, right? Right. So when we do a blue step, we don't care about the edges between here, so we don't need to change Y. Okay? And we don't want to change Y, right? We don't want to lose a factor of 2 because we're not adding a vertex to our book. Right? So we really want to keep Y the same. Okay, this is our basic, the basic 2 things we might try to do. Okay, I guess we might say, okay, well, if you pick a vertex X, if it has more than half neighbors that are red in X, then you do the red step. If you have more than half blue, then you do a blue step. And maybe we can guarantee that everyone has at least half red across. Okay, so at least that part isn't so terrible. So let's, or at least to think. So why it might not be so unreasonable to think that every vertex here has at least half red across. So we're given the coloring, we have no choice. Yeah. Right, so you could get a vertex that had very low red degree across. What do you want to do with that vertex? Yeah, right? So we'd be very angry at it, or you could just throw it away, right? So we have this sort of basic technique available to us that vertices on the left that have low red degree across, we can just discard. So why is that okay? Well, it's bad in the sense it decreases the size of X. But suppose it decreases the size of X a lot. Suppose you throw away lots of vertices on the left that had low red degree across. What would that do to the rest? It would increase the density, right? So the other guys would have larger red across, and you'd be kind of happier, right? Because then for all future times, you have a bipartition with larger red density.
Unless you were already completely blue, then you're dead.
Completely blue where, sorry?
Between X and Y. If you're blue,
Ah, right, yeah. If your red density has gone down, you're in bigger trouble.
yeah.
Okay. So let's say that the red density across is P. And so what can we say about P? So P is going to be the red density. So I'm going to write ERXY over X times Y. Okay? And so P0 is the value at the start. With the P0, we can assume it's at least a half. Right. So that's our basic setup. Right, this is just by symmetry. We pick red to be the color that is density at least a half. When you take a random bipartition, you still keep the expected density across the same. Okay, and this is the current density after a while. So what we want is that this doesn't go down too much. Right, so it's utterly crucial. Like the most crucial thing for us is going to be trying to keep P close to a half, or larger. Larger is fine. Right, not letting it drop. Okay, but if P is decent, if it's close to a half, then we can throw away low degree vertices, and we're going to get a boost, and we're happy with that. That gives us a win. So later on Friday or next week, I'll do all these calculations carefully, but hopefully you believe that actually we win by a lot there. It's not well, okay, modulo something important. Right. Okay, so that's not such a big deal. So now we're in good shape, right? Now, by this min degree condition, we have a big neighborhood over here, always. Every vertex does. So if it has neighborhood at least half, you do a red step. Neighborhood at least half blue, you do a blue step. Everything's great. Why are we not done? So what can go wrong? Right. Problem. What if P decreases? Right. So, for example, we replace x and y by the red neighbourhoods here. How do we control the red density between these red neighbourhoods? In a blue step, similarly, we're going to the blue neighbourhood here. How do we control the blue neighbourhood to the whole world, the blue density? Can we at least do that one? That one's not quite so bad because we're not changing y, right? So if we have this min degree condition, then at least puts a lower bound on how much we can lose. Actually, it doesn't quite work, but we'll see later how to fix it. Okay, so that doesn't work as is, but it's not actually very hard to fix. So I haven't told you how to fix it yet, but we will fix it. Yeah?
So for now, we do the red step if we have these neighbors.
Right. So the first attempt, the first idea would be do the red step. You have at least this many red neighbors, and do a blue step otherwise.
And otherwise, we do.
Yeah. So actually, well, this half is sort of very well motivated. This half is not so obvious, and actually, it's not the right thing to do. There's no real reason to do a half here, other than to copy Edi Separation, right? But we don't have symmetry anymore, right? Red and blue are different now. So actually, what do we care about? How many blue steps are we going to do? We're going to do at most k blue steps, right? And how many red steps we're going to do? We're going to do t red steps. And we'd like t to be big, right? And so this gives us an asymmetry that, well, at least we have some chance of exploiting.
Are we not going to decrease A or B at any point?
No, we're only going to increase them. Yeah, when something's there, it's there forever. Yeah. Yeah, yeah. Changing your mind is a bit scary. Yeah. Right. Okay. So right. So the problem is, so the whole world is P, but look at between here. What if this is less than P minus alpha or something? And yeah, how large should alpha be so we're worried? Well, we're going to do t red steps. We want t to be constant times k. So, and we want p to say close to a half. So alpha should be smaller than 1 over k. Right? That's the kind of scale that we can cope. So alpha is going to be approximately, you should think, 1 over k. Maybe some small constant times 1 over k. No, I'm already going to write an epsilon. Okay, if it's epsilon over k, then we're safe. Okay? Okay. So we can only allow it to go down by this much, which is really not very much at all. And why shouldn't there be some correlation between the density of red edges between these big sets and the red neighborhoods, and the red graph inside here? So we first thought that maybe there shouldn't be, but then we easily came up with a construction where there was. And then we were like, okay, but this construction's silly because this is like superstructures on this side. So we're like, okay, if there's superstructure on this side, you just win. So we're okay, maybe if this happens, it has to be superstructured. Then we came up with a construction where it was really not very structured at all on this side. And yet this happened. So that construction turns out to be, in fact, basically the same as the Kahn-Kalai counterexample to Borsuch's conjecture. So, which pops up beautifully here and really makes life difficult. Okay, but then you have a conjecture that maybe that's the worst thing that can happen, and that's our conjecture, and it's still open. So we, yeah. So 5 years pass. And we're basically stuck on how can you deal with this issue. So I'll talk at the end more about some of the ideas from those 5 years. But anyway, so we were basically stuck. And then in sort of January, Simon says, okay guys, okay, so we're basically stuck, but maybe we can do off-diagonal Ramsey numbers. Okay, so how about, okay, off-diagonal. Okay, so why would that be the case? So what I'm talking about is RKL, and L is some small constant times, so some small constant times K. Let's say K over 100. Okay. Okay, so why would it be useful for that? Okay, so what is this? What is this structure that we really want here? Like, how are we using it? The reason we would like structure here, or structure across, is what we'd really like to find is when this kind of thing happens, everywhere, then you could pass to a subset here and a subset here, where you have higher density. Right? You'd like to say, okay, I'm willing to give away a fraction of my world here, and a fraction of my world here, as long as I get much higher density. Right? So, why is it? Let me draw it in a slightly different way. Okay, so let's put this x maybe here now. Or I don't know. Yeah, so this, yeah, whoops, x here, and then think about this being a sort of red neighborhood, and red neighborhood, and blue neighborhood, and blue neighborhood. Right. And what we're saying is here we have sort of p minus alpha. We're losing a bit in the top.
What is this white point? It doesn't lie in any of these sets.
Yeah, sorry. I just don't want to draw it inside the set. Fine. Okay. X is here. Yeah, because it's not in either the red or blue neighborhood. So x is in X. And this is its red neighborhood and its blue neighborhood. And then that's its red neighborhood and its blue neighborhood over there. Sorry, that's why I drew it in the middle. Right. And what happens here between these two, you know, you have sort of a density p minus alpha. Right? The right way to density.
Just the
Yeah, just from the red neighborhood of X to the red neighborhood of X, which is what we want to do. We want to do a red move. And so let's assume here that actually the red neighborhood here is, you know, it's pretty big. So we do want to do a red step. And this is like half and half, right, as usual. Right. So how large are these two? Okay, so perhaps to think about that, let's go back to the Eddy-Seckeresh proof. Right, to remember what happened in Eddy-Seckeresh. So now in Eddy-Seckeresh, let's try to prove RKL is at most K plus L, choose L. Okay, so we can do the same thing, the same algorithm, but now we can make a different choice about when to put in A and when to put in B. And maybe I'll go over here for a second. Yeah, suppose I can erase the comic slide. Right, so in the usual proof of Fedor-Sekaresh, what do you say? You say pick a vertex X, look at its red neighborhood and its blue neighborhood. It's over here. Right, and this is like RK minus 1L, and this is RKL minus 1. Right, otherwise you're done. Right, so the size of the red neighborhood, so if the whole world is like K plus L, choose L, right? We have to compare that to the size of this thing, or the bound on it, which is K plus L minus 1, choose L, and that's basically K over K plus L times that. Exactly. And similarly, K plus L, choose L, is L over K plus L times K plus L minus 1, choose L minus 1. Okay, so at least in the Eddy-Sekaresh proof, the ratio you're interested in is this guy. And so gamma equal to that guy.
Isn't it inverted?
Probably. Thank you. Did I get it right now? Now this is wrong. Third time lucky?
No, I think
No, it's okay. No, great. Okay. Okay. Okay, so you do a blue step if your size gamma proportion of the world, you do a red step if your proportion 1 minus gamma. Right. Okay, so the blue density inside this set should have size roughly gamma times x. And the red neighborhood should have size roughly 1 minus gamma. Right, that should be our cutoff to decide whether to do a red step or a blue step. Right, like in Eddy-Sekaresh. And gamma is now small, right? We're now thinking of gamma as being sort of less than 1 over 100, let's say. Okay? Oops. We gave up on gamma as a half. We're going to try gamma as 1 over 100. Okay. Why did that help us?
you didn't say like we want to do a red step, so it should be like bigger than 1 minus gamma in the red.
Yeah, right. So yeah, so we're in a situation where this is at least 1 minus gamma, exactly.
Okay.
So we want to do a red step. So this is at most gamma, exactly. Right. What are we going to do? So we know that overall the red density is P. Maybe to make it a bit simpler, let's pretend that every vertex has density P going across in both directions. Has P times, every vertex on the left has P times Y neighbors, red neighbors, every vertex on the right has P times X, red neighbors. What you know is, between this set and this set, you have density P minus alpha. Where is your density boost?
Is it like between the blue neighborhood of X and the...
Exactly. what can you say about, let me draw them in orange, this guy and this guy? What can you tell me about the red density between those two sets?
Becomes larger.
Yeah, how much larger is it? I'm gonna I'm gonna erase and reorganize while you think about how much larger it is.
Plus alpha times 1 minus gamma over gamma.
Say it again.
B plus alpha times 1 minus gamma over gamma.
There you go. Exactly. Here, from here to here. So maybe I'll write it over here and store it over here instead. So 3, a density boost step. Added a move to our arsenal. So what do? We choose x and x, and we're going to do a blue step, right? So we're going to replace x by this guy, and y by this guy. And what do we do with x? Where should we put it? In B, right? Because we're replacing it by this guy, so we can put it in B. Exactly. X and x. We update as follows. A becomes A. Maybe I'll put it here. So B becomes B union X. A stays as A. X becomes the blue neighborhood of X, intersection X. And Y becomes exactly the red neighborhood of X, intersect Y. And what happens to P? P goes to at least P plus alpha times 1 minus gamma over gamma. Yeah, right. So let's count, we just count red edges. So how many red edges are we losing between here and here? Alpha times 1 minus gamma times a half.
We assume that
Yeah, sorry.
the density becomes small if we do.
Right. So if the red density were bigger than p minus alpha, we would do a red step. If the red density is smaller than p minus alpha, then instead we want to do a density boost step. And then because we've lost alpha times this many, because they're concentrated on this much smaller set, we've gained much more in the density. And because gamma, remember, is like 1 over 100, this means we've actually gained like 100 alpha. So we've risked going down by alpha, and in return we've gone up by 100 alpha.
Okay, but there's like a subtle trade-off because your blue neighborhood could be like really, really small, but then the density is like really high.
Absolutely, exactly. So really, this is something even better or worse, depending on perspective. You get 1 minus beta over beta for some beta at most gamma, where the neighborhood, the blue neighborhood x intersect x has size beta times x. Right, so whatever proportion of blue neighbors, and it's a most gamma, because you're doing this step, you gain that much in the density. So the smaller you go, the more you gain the density. Now, okay, you might worry, okay, what if you take beta really, really small, x disappears? I mean, you can't, because this can't go above 1. Right? So as long as your alpha is not crazily small, there's a lower bound on like how small this neighborhood can be. Okay, so now we have basically all our moves. So the next crucial thing to tell you So we're not quite ready yet to define our algorithm because we chose alpha, but this alpha doesn't work. So why did we choose alpha to be this? Well, because we were worried that the enemy might just do red step, red step, red step, red step. We go down by alpha every time, and then we end up with a p that's less than a half, and then it goes, haha, now I'm going to decrease y by too much. We didn't want it to be any smaller than this, any sort of bigger than this. But how much density boost are we getting from this? We're getting, 100 times as much, say. But 100 times epsilon is still small. And how many of these density boost steps are we doing? Well, every time we do one, we add a vertex to B. And now B has size not at most k, but at most, oops, I can't write. I forgot to write an L. Other way around. I can't write an L. There we go. What's my brain? I had like a mini stroke or something. Yeah, maybe that's why. Yeah. all the signs coming together. Yeah. If I collapse at some point, then you'll know. Right. So B is only going to have size L, which means what? Which means, right, the total boost you get is L times this guy. So this over gamma times k. Gamma times k, it's over there, is roughly L. So basically the total boost you get from all this is just epsilon. So all this boost is just going to raise your p by epsilon, and that's really not doing much for you. Right? So maybe the enemy just does, okay, fine, I'll just do L boost steps, and you're in trouble. Or you've gained nothing, basically. And note, these boost steps are painful to us. Right? We lose half of the right-hand side every time it happens. So our dream of finding this book of size 2 to the minus t times, right? Remember the book we wanted to find. I'll write it here. The book we want to find, this red book, which is going to be A on the left and Y on the right. This is going to have size t, and we'd like this to have 2 to the minus t times n. Right? That's our dream. So we've definitely lost a factor of 2 for every guy here. But we're also losing a factor of 2 every time we do this. So actually what we're getting, and there could be L of these things. So actually what we're getting is not this, but it's minus t minus L times n, and that's a total disaster. Right? That's just catastrophe. It's the end of the world. So we really can't afford it. So this alpha is bad. Okay, so we're once again stuck. So what should we do? You all had the advantage of seeing Simon's lecture last week, so you'll know already what we do, right? I'll give a... You do this. Right? Yeah, change alpha, but yeah, to change alpha... Yeah, let's do alpha online. Right? We don't have to use the same alpha in every step. This is not really alpha. Our alpha is really alpha of p. So I'm going to get rid of this, because it's not at least a half anymore. An alpha of p, which is going to be what? Well, it's going to be at least epsilon over k. But if p increases, then we have more room to play with. Right, so as we start, this is p, this is p0. We're sort of super scared of going down below p0 minus epsilon. This is like death zone. Right, and so we're like, oh, I don't want to go down. But maybe the enemy does a bunch of density boost steps. We're like, oh, now we're here. Okay, okay, so it's fine. But now we can afford to bet twice as much, right? If we're twice as high up, then we don't mind going down like twice as fast. Only worried about going below this line. Okay, so maybe we go down twice as fast, and that's fine. But if we then go up, if our alpha is twice as big, then we also go up twice as fast. And now we're even higher, and we can afford to bet even more, we go up even more. Right? So our alpha can basically be proportional to how far above P0 we are. Okay? So we're going to do that. I'm going to say plus epsilon times P minus P0. So what we do in the paper, and what I'll do when I actually write in the details, is slightly different from this. I might try and write in the details with this. Who knows? We'll see. But anyway, this is what you should be thinking, basically, right? The amount you bet is like it's an epsilon proportion of how far you're above where you started. Plus a little bit, because you don't want to bet 0 at the start, right? You want to bet something. And that's all you can afford to bet. Okay. So now, maybe I can actually state the algorithm. Right. This drawing's a bit of a mess now, isn't it? Is this helpful? Shall I leave it or shall I erase it and leave it? Okay. Okay. So. Okay. So, what is the book algorithm? Right, so we're given a coloring of EKN, given sets of vertices. We start with A equals B is empty. Sorry?
The density between x and
right, and P0 is the density of edges, density of red edges between x and y. That's all.
Are you defining red to be the minority color?
Yes, so what we will do in practice, because we're not diagonal anymore, right? We're now off diagonal. So we've got an L and we've got a K, and L is now quite a bit smaller than K, potentially. So we have to choose what to do. So what's actually going to happen is, okay, so we're going to have a K and an L, right? And we want to find the book in red, right, in the color which is large in K. But what if the red density is just not good? What if it's lower than it's supposed to be? We want it to be 1 minus gamma.
It should be easier to find a blue link in this situation, right? Because it's much denser in blue.
So right, so there's
Quite close to diagonal, sorry, yeah.
so we anywhere we like, but suppose the density is not what we'd like it to be. So is it about 1 minus gamma? We'd like it to be 1 minus gamma. Or at least 1 minus gamma. If it's smaller, then we're going to be in trouble finding this red book, because y is going to shrink too fast. So in that case, we're not going to want to just do this. We're going to want to prepare ourselves a little bit. So what would you do in that situation? Suppose you found you had a coloring which was a bit denser in blue than you wanted it to be.
Can you just like do some blue steps for speed?
Exactly. So we can just do blue Eddy-Shekhar steps. Suppose it's 1 minus gamma minus delta. So the red is 1 minus gamma minus delta, so blue is gamma plus delta. So you're gaining a little constant factor for every blue step you do. So if you do lots and lots of blue steps, when you're gaining a constant factor each time, you've already won. You're super happy. if at some point you find that you have the right red density, you can do this, and you're further away from the diagonal than you were at the start. Right? You start, your L is much smaller than K. You take blue steps, your L is shrinking. Right? Every time you take a blue step, the L you're looking for is going down by 1. So you're going further and further away from the diagonal, and life is getting easier and easier for us. Okay? Yeah. So life for us is just, the further from the diagonal we are, the easier our life is. Okay, so I'm going to assume, or you should think, that the density is 1 minus gamma. In practice, it will be a little bit smaller. But there'll be some balancing at the end when we do calculations. Okay, but for the algorithm, it's just anything. It's just whatever happens to be. Okay, so we're given some P0. Okay. And right, remember that alpha of P is going to be epsilon times P minus P0 plus 1 over K. And there's also going to be a mu, which is just going to be some constant. Okay? Which, if you like, you can think of it as being gamma. But it won't always be gamma. Okay. So what do we do?
Sorry,
Yeah.
what is
You'll see in a second. If you like, you can think of it as being gamma. So what it's going to be is, it's going to be how we choose which step we do. Yeah. So, another one is repeat the following steps. Until size of x is small. And small for us is going to turn out to mean something like this. Okay. So this is going to turn to be useful for us. If you like, you can think of this as being just 2 to the little OK. Sorry, this is something that's much, much smaller than what we started with. Okay? And this will turn out to be what we need in order to keep the thing running. Okay, so some Ramsey number. Okay? So, 1 is degree regularization. Which just means remove vertices of low degree. Okay, so let me not tell you yet exactly what this means, because it's a little bit delicate. Okay, so it actually means 2 different things. Well, okay, so we need it for 2 different reasons. One of them, so the one I'm going to tell you about first, which I've already told you about, is you want to make sure every vertex here has a decent sized neighborhood over here, right? So wherever you pick here is going to have enough red neighbors over here. For that, low just means sort of P minus little o1. Okay? So nothing, like really, things that are way smaller than they should be, throw them away. If there's lots of them, your density goes up by miles, you win by miles, everything's super chilled. There's another reason which is going to make it a bit more subtle, but I won't say that yet. Okay? So anyway, so we'll discuss in a minute what low means. 2, if, right, so I guess I haven't quite motivated this properly yet. Yeah, so perhaps actually maybe it is a good time to talk about that. How long do I have?
Is low red degree 2y, right? Just to be sure.
To y, sorry, yeah. Thank you. Thank you, exactly. Okay. Okay, so let me write the incorrect thing first, and then we'll fix it. So if there exists an x in x such that the blue neighborhood of x intersect x is at least mu times x, then do a blue step. That is,
You will do step, right?
Sorry? Yeah. So you put x in B and replace x with the blue neighborhood of x and just replace y with y. Okay. Who can spot the problem?
Only these kind of steps, then
Yeah, so we're kind of okay with these steps because we're, we put there's only L of them, right? Each time we lose something, I haven't said what mu is yet, but as long as mu is reasonable, then they won't destroy x by themselves.
You have no control, like the density between.
Right. The problem is not that. It's not the size. It's the density between here and the whole of this world. And what control do we have? What's our lower bound on the red density between this neighborhood and y?
You didn't say what low degree means.
Yeah, it's this. Exactly. This is our lower bound, right? It's the only thing we can say is that we got this minimum degree. That gives us a lower bound, right? So we can't actually afford this low degree to be very low. So we know this low degree. So if we don't want the density to go down too much, we don't really want this to be much bigger than alpha. So is this like p minus alpha then? The trouble is, we want a big density boost step, right? We want the density boost to be like 100 alpha. And we'll only get a density boost of 100 alpha by going down to a set that's much, much smaller. And okay, that is what's happening in these blue steps. We're going down to a set that's much, much smaller and gaining 100. But that's only okay because there's not so many of them. Whereas the degree realization, there could be lots of them. Right? There could be as many as k or k plus l. So this is actually a problem. Right? We need to allow, say, alpha over gamma or something in order to be able to control how many vertices we lose in these steps. We just have a large constant times alpha. But now the density is going down in a blue step by 100 times alpha, which is a disaster. So we need one more idea. I think it's not very obvious. So we need to do many blue steps at the same time. So instead of just doing one blue step, suppose we could do many blue steps. So what would that mean? That would mean that instead of just adding one vertex to B, maybe we could find a bunch of vertices we could add to B, some S. They better be a blue clique, because we're going to add them to B. And when we add them to B, we're going to shrink X into the common blue neighborhood. this is now a familiar object. So what we want to find is a large blue book. It turns out this is not actually very difficult to do, surprisingly. So enlarge in the sense that we care about follows by a simple counting argument. I guess I'll do that maybe next time, because I'd like to finish the algorithm in the next 8 minutes. OK, so next time I'll show you how to do this. So, right, so we actually do get something like this. Not exactly this, but I'll define it next time. So this is called 2 is a big blue step. What does that mean? So if it's not enough to have one vertex with good blue degree, we need to have at least Ramsey k L to the 2/3 vertices x and x. Yeah, so such that, such that. The neighbour is at least mu times x. There's many vertices of high degree, then we can do a big blue step. Then add, actually we can add something like L to the 1/4 vertices to B. Okay, so I'll show next time how we do this.
These vertices need to be like on a clique.
Yeah, so we're going to add a clique, a blue clique of size L to the 1/4. And we're going to shrink X to their common blue neighborhood. I'm going to show that the shrunk set has size roughly mu to the number of vertices we put in here. Okay, so it's shrunk by the correct amount. And this will turn out not to be as hard as it sounds. It will actually be just simple counting. Right. Okay. So that's if there are many vertices of high blue degree. If not, note that this number is much bigger than this one. Right? So the 3/4 and the 2/3. Yep.
So the neighborhood shouldn't be like something like mu to the power of the vertices where you're adding?
Yeah, sorry. So this is the neighborhood of each vertex. What we'll find is,
Okay, you will do like 30.
yeah, this will be like you don't do it inductively. You do it by some double counting. But yeah, it's a nice exercise. Yeah, I don't know if maybe you can do it. This is like mu to the b times x, basically, roughly. So you can find something of the correct size. There's more over a clique, and you do it using these guys.
Why is it L or 1/4?
L to the 1/4 is something that's smaller than L to the 1/3. Yeah. So basically, that's another clue of So basically, there's an error term here. The error term is something like e to the minus L to the 1/4 squared over L to the 2/3 or something. Right? I just want this to be close to 1. Yeah. So there's a lot of space here. It's not and all we really need here is it's much bigger than 1. We don't really need it to be L to the 1/4. It's just okay. And all we need is this number is smaller than 1, this number is smaller than that one, and this one's smaller than half of that one. So it could be almost a half, if you wanted. Okay. But yeah, maybe try and see if you can do this before Friday. Okay, next thing is we choose a central vertex. X and X.
Can you repeat the previous step?
Yeah.
Then add L to the power 1/4 vertices to be each L to the power
Yeah, we're going to choose some special. So what we're going to do, I want to try to fit it in here. Maybe I'll fail. So what we're really going to do is, so here's x. We're going to throw away these. We're going to look inside these vertices, and we're going to find in here a set S, and in here a set T, such that this is a blue clique. This is complete blue. This guy has size B, which is at least L to the 1/4.
Okay.
And this guy has size mu to the B times X, maybe over 2 or something. Whatever, some almost that size. Okay? And then we add this set to B, and we replace X by this set. Right? And it's shrunk by the correct amount. You'll think of mu as being the amount we're allowing ourselves to shrink in a blue step, which you should think of as being gamma for now. Okay. Does it make sense? Yeah, and I haven't told you how to find the structure, but this is your homework, is to try and figure it out. And then I'll tell you on Friday. Yeah. Okay, so now we're going to choose a central vertex. Maybe I'll go over time slightly just to finish the algorithm. How are we going to do this? Well, we want it to have low blue degree, so avoid these guys. Now there's very few of them, so it's easy to avoid them. And we also want something a little bit subtle, I'll talk about next time. We want the density of red edges between the red neighborhood and X to be very close to P, not to be too small. Right? Because the whole idea of this density boost was minus alpha here means plus alpha times something here. That's not true if the red density is smaller. But you can do that easily just by some convexity, so counting paths of length 2 on the right. So we'll do that next time. Okay? So it's another very easy argument. Allows you to pick an X that has good red density. Now 4 is you do a red step. This is if the red density is at least P minus alpha of P. Right? So the red step means, remember, we go into the red neighborhood here, which is now size at least 1 minus mu. Right? Because there are a few vertices with large blue neighborhood, and we picked a vertex at a large red neighborhood. We go into the red neighborhood here, and the density across here is at least P minus alpha. If it's at least P minus alpha, then we do a red step. Huh? Is that okay?
We're fixing an X vertex, right?
Yeah, we choose an X in this step 3.
Oh,
In a way I didn't exactly tell you, but it's going to have large red neighborhood here. Right? So this is if the red density between the two red neighborhoods is at least this, then we do a red step. We haven't lost too much. And 5, otherwise, do a density boost step. Which, if you remember, means going into the blue neighborhood of X here, into the red neighborhood of X here. Right? And getting a big boost in our density, because this was small, and the density here was small. Okay? And that's the algorithm.
No, because this only happens until X is less than or equal to R.
Yeah, so then we just stop, and we say, okay, now we have a set A and a set Y. That's our red book. Yeah.
Otherwise, we found a clique or a Brooklyn.
Yeah, right. Sorry. Yeah, perhaps I should have assumed here a coloring with no red KK or blue KL. Thank you.
But wait, now this is a contradiction, right? Because you're definitely going to find red KK if you find it.
Right. So yeah, we're not quite going that far, but yes. So I guess we're going to get a contradiction. So suppose you're given a coloring with no KK or KL. This algorithm will give you this book, and then maybe it's contradiction, or maybe it's not.
This mu is fixed since the beginning.
Yeah. So this mu will be fixed throughout the algorithm for this course and in the proof. Yeah. If yeah, so there's one change that one might make in the future. For other applications, you might want to change mu as you go. Also, we should think of mu as being gamma. So if gamma tends to 0, I don't want to deal with that. I'd like mu to be fixed. So for us, mu will be really just a fixed constant.
You only go to 3 if the big blue step is not.
Yeah, sorry. So after these, if not, go back to the beginning.
Oh, okay.
So 2, you go back to the beginning. If not, then you go to 3, then you go to 4. You only do 4 or 5, right? So you don't do Yeah, sorry. So yeah, I didn't quite.
4 and 5, you do according to the exact coordinates, right?
Sorry. Say again.
No, the step 4 and 5.
Yeah.
You do according to the x that you choose.
Yeah, you do it using the x, and you do either 4 or 5. Yeah, exactly. Depending on the red density between the red neighborhoods of x on the left and right.
And every time you do a step, you need to do the regularization.
Every time we do exactly. So we do regularization step, then blue or red or density. Then regularization, then blue or red or density. Yeah.
Okay.
So all of the odd steps are regularization, all the even steps are one of the other 3. Yeah, exactly. Yeah, I didn't quite say exactly how we do this, but yeah, it's sort of, it's also, there's quite a bit of flexibility in exactly how you do it. But yeah, it should be a much bigger jump than alpha, and small enough so that this is, so the blue ones don't matter. Right, okay, only a few minutes over. So on Friday, we'll start again here, and then I'll I'll do the big blue steps properly, I'll do choosing the vertex properly, and I guess maybe I'll prove the density boost step properly. And then maybe next Wednesday we'll be able to actually prove something. Cool. More questions? Okay, see you on Friday.